Okay, so we now covered the background material of set-valued operators and monotone operators. Now let's move on to discussing methods to find zeros of these operators. Let's discuss the notion of non-expansive and contractive operators. So we say an operator T is non-expansive if this non-expansive inequality holds for all inputs x and y. To put it differently, non-expansiveness is by definition equivalent to 1 Lipschitz continuity with Lipschitz coefficient L is equal to 1 for the operator. And we say an operator T is a contraction if it is L Lipschitz with the Lipschitz parameter being strictly less than 1. Mapping a pair of points x and y by a contraction reduces their distance, and mapping by a non-expansive operator does not increase their distance. So two distinct points x and y will have a certain distance measured by this norm. Now, when we map these 2 points through the operator t, tx and ty, those are the outputs of the points, input points x and y under the operator t, and the output points have a distance less than or equal to the input points x and y if the operator t is non-expansive, and the distance of the outputs are strictly is strictly reduced if we have a contraction. Okay, so here are some properties of non-expansive operators. If t and s are both non-expansive operators, then t composed with s is also a non-expansive operator. If t and s are non-expansive, and if one of the two operators, t or s, if one of the two operators are furthermore contractive, then the composition is a contractive operator. If t and s are non-expansive operators, then a convex combination of the two operators becomes a non-expansive operator. And if t and s are non-expansive and t is furthermore a contraction, then a convex combination where the component, the theta multiplied to t, is strictly positive, then this becomes a contraction. So these 4 statements can be proved by by using the definition of non-expansiveness, contractiveness. It's a basic analysis exercise. So if these statements are not obvious, then maybe it might be worth trying to work these out. Okay, so the notion of non-expansiveness and contraction is quite standard throughout all of mathematics. But in this class, we will rely heavily on the notion of averaged operators, which is not as widely known as the notion of contraction or non-expansiveness. So let me define what an averaged operator is. For theta being for a certain value theta being strictly between 0 and 1, we say t is a theta averaged operator if t is a convex combination of the identity mapping and another non-expansive operator s. So if we take a non-expansive operator and take a convex combination, a strict convex combination with the identity operator, then that gives us an averaged operator. And we say an operator is averaged if it is theta averaged for some unspecified value of theta between 0 and 1, without excluding the boundaries. An operator is firmly non-expansive if it is 1/2 averaged. And so the terminology firmly non-expansive is coined because 1/2 averaged operators arise quite frequently due to the resolvent, which we will talk about soon. If an operator t and s are averaged, then the composition ts is also an averaged operator. Now this fact is actually not that obvious. So the proof is somewhat complicated. It's something we will deal with it later in chapter 13. And averageness is, again, it's not as commonly known throughout the broad mathematics compared to non-expansiveness or contractiveness, but it's the basis of convergence of many splitting methods that we'll discuss in this class. So here's an illustration of the notion of contractiveness, averageness, and non-expansiveness. So note that here the set of contractive operators is contained in the set of average operators, and the set of average operators is contained in the set of non-expansive operators. So we could perhaps write contractive includes average, and then that includes non-expansive operators. So what I want to illustrate specifically through this through this illustration is that the notion of averageness is an assumption. It's a weaker assumption compared to contractiveness, because if an operator is contractive, then it is an averaged operator, but an averaged operator is not necessarily a contraction. In terms of assumptions, in often cases, we will assuming an operator is contraction will be too strong of an assumption, so we will instead assume the operator is averaged. Now, these figures actually have a specific meaning. So, and the specific meaning is related to the scaled relative graph, the SRG, and that's a topic that we will discuss more in depth later in chapter 13. All right, let's move on to the fixed point iteration. All right, so what's a fixed point? Well, a vector x is a fixed point of an operator t if x is equal to tx. So if we take the point x and feed it into the operator t, if the output is x itself, then we say x is a fixed point. We write fixed t for the set of fixed points. So this is the set of x's such that x is a fixed point. And a different way to express the set of fixed points is that this is the operator I minus t. We take the inverse of that, and then we provide 0 as the input. The set of fixed points may contain no points. So, for example, if we consider the operator t, that takes a scalar input x and then increases the value of the input by just value 1, or for whatever positive value, then this is we can think of this as a shift operator, and the shift operator, well, that operator doesn't have any fixed points. It's also possible that an operator can have many fixed points. So tx is equal to absolute value of x. Well, if the input x is positive or it's non-negative, then that becomes a fixed point of this operator. So a fixed point can be unique. There may be no fixed points, or there could be many fixed points. Interestingly, when an operator t is non-expansive, its set of fixed points is closed and convex. It could be empty, so we're not asserting that the set of fixed points is non-empty, but in any case, whether it's empty or not, because an empty set is a closed convex set. So whether the set of fixed point is empty or not, it is a closed convex set. The proof of this assertion is not too complicated. It's written out over here, but I'll skip over the proof of this assertion in this lecture. Okay, next let's talk about the fixed point iteration. So the fixed point iteration, which we abbreviate as FPI, is defined by this. So the k+1th iterate of the iteration is defined as the operator t applied to the kth iterate of the iteration. And this iteration is defined for value k being k equals 0, 1, and then ... And the initial point x0 is just some starting point. And we assume that the operator t maps from Rn to Rn. In particular, the domain of t is all of Rn. The fixed point iteration is used to find a fixed point of an operator t. And clearly, the algorithm stays at a fixed point if it starts at a fixed point. So there are two steps to using a fixed point iteration. The first step is to find a suitable operator whose fixed points are solutions to a monotone inclusion problem of interest. So the setup that we're considering is that we want to solve a monotone inclusion problem, and therefore we want to find a fixed point operator such that its fixed point correspond to the solutions we're interested in. And the second step of using a fixed point iteration is to show that the iteration actually converges to a fixed point, because in general, fixed point iterations need not converge. In this class, we provide two convergence guarantees. The first one is the more commonly known one, and that is we have convergence when we have contractive operators. So if the operator T is a contraction with a contraction factor L strictly less than 1, then the fixed point iteration is also referred to as a contraction mapping algorithm. Then for any fixed point, then for the fixed point x star, the distance from xk minus x star is by definition equal to t xk minus 1 minus t x star, because x star is a fixed point, so x star is equal to t x star, and this is less than equal to L times xk minus 1 minus x star by contractiveness of the operator T. So chaining this argument, so through this argument we get this inequality, and chaining this argument we get the distance from xk to x star is L to the power k times the initial distance to the solution. So this argument, this geometric convergence, is the basis of the classical Banach fixed point theorem. So this argument it's not too complex. It's relatively straightforward. So when the operator T is a contraction, then the convergence, the question of convergence, and the rate of convergence becomes a simple matter. The problem, though, is that in many optimization setups, assuming a contraction a contraction operator mapping is too much to ask for. Therefore, we want to have another convergence condition under weaker assumptions. All right, so now this is the weaker condition. The fixed point iteration converges when the operator is averaged. So more specifically, let operator T be an averaged operator with a theta average operator with some value of theta between 0 and 1. Then the fixed point iteration is then referred to as the averaged iteration, or the Krasnoselski-Mann iteration, or the KM iteration. Now, Theorem 1 is a central theorem to this class, because in this class we will not be proving that many theorems, or at least we'll make many mathematical statements, we'll prove many mathematical statements, but we'll have really a handful of theorems that we state very formally, that we emphasize as to be important, and then that we will subsequently formally prove. Theorem 1 is so important in this class because basically all of the algorithms, or not all, but most of the algorithms that we consider in this class will eventually be reduced to a FPI, to a fixed point iteration. And then once the algorithm is viewed as an instance of the FPI, then we will then proceed to establish that the corresponding operator is an averaged operator. And once that is done, then the convergence of the algorithm will be established by appealing to Theorem 1. So basically, most of the algorithms that we consider in this class, their convergence will be established by appealing to Theorem 1. Okay, so what's Theorem 1? Theorem 1 states that assume an operator T is theta averaged, with theta being 0 and 1, and we assume that a fixed point exists. We don't prove that a fixed point exists, we'll just assume that a fixed point exists. Then the fixed point iteration with any starting point x0 converges to a fixed point. So in other words, the iterus xk converges to a limit x star, and this limit x star is a fixed point of the operator. Here we say the sequence converges to one fixed point because when the underlying operator is an averaged operator, then it's possible that there is no fixed point, but we assume that a fixed point exists. So the fixed point could be unique, but there could be multiple fixed points. So if there are multiple fixed points, then We don't say which fixed point we converge to, but we do claim that we converge to one single fixed point. Furthermore, these quantities are monotonically non-increasing. So the distance of the iterates to the fixed point, the difference between the current and the subsequent iterate, and then the distance to a particular solution is monotonically non-increasing. So I should say is monotonically non-increasing. And finally, the distance of our current iterate to the fixed point set converges to 0. And then the distance between the current and the next iterate actually converges to 0 with a rate. So xk plus 1 minus xk squared has this rate, and note that this is order 1 over k. Okay, so Theorem 1 is a big theorem in the sense that we use it a lot. It contains many statements. So Theorem 1, the purpose of Theorem 1 is to characterize the convergence property of the FPI when we use an averaged operator. Okay, so before we prove the first theorem, let's make a few points of discussion. If we are given an operator that is non-expansive but not necessarily averaged, then we can perform averaging ourselves. So we can form this operator, which is so given operator t, we perform this averaged operator ourselves with a particular value of theta that's chosen by ourselves, and then we can use the fixed point iteration with this operator, because the set of fixed points for the operator t is the same as the set of fixed points for this operator. So the parentheses should go here. So by performing averaging ourselves, we retain the same set of fixed points, but now the operator, which used to be merely non-expansive, now becomes an averaged operator, and therefore the convergence condition, convergence guarantee of Theorem 1 applies. And using this operator really provides us, we don't incur any additional computational cost when we are to implement the algorithm. So by performing averaging, we basically get a convergence guarantee when the operator is non-expansive without paying any cost. So for example, as an example, this operator, so the operator from R2 to R2 defined in this way. So T of x is defined by this matrix matrix vector product. So this operator is actually theta averaged, with theta being equal to 3 over 4. And the set of fixed points is this vertical line going through the origin on the 2D plane. And then if we perform a fixed point iteration from this starting point, then x0 goes to x1, then it goes to x2, x3, x4, x5, and then it will converge to this limit point. So the set of fixed points is not unique, but given a starting point, the FPI converges to one fixed point. And I think through this example, it's quite clear that the limit will depend on the starting point x0. So in this particular example, if we were to start from this point as x0, then the limit point will be over here. All right, then let's move on to prove Theorem 1. But before we start the proof in earnest, let's first outline the proof. So I'll explain the key argument. Let's assume that there exists a non-negative sequences v0, v1, ... and non-negative sequences a sequence s1, s0, s1, ... And let's assume that these sequences satisfy this inequality. Okay, so vk plus 1 is less than or equal to vk minus sk. So if these sequences satisfy this inequality, then the consequences are that vk, the sequence vk decreases monotonically, because if you look at this, well, vk plus 1 is less than or equal to vk. So vk is a monotonically decreasing sequence, but that doesn't necessarily mean that vk converges to 0. And here I should say monotonically non-increasing. So it is possible, so the vk's sequence is decreasing, but it is possible that the vk sequence decreases to a positive value, and that actually does happen quite often. So that's not a pathological situation, that's actually just the usual situation. So we have no expectation that vk will converge to a 0. However, what does converge to a 0 is sk. This sk sequence converges to 0. Okay, so let's see why. To see why sk must converge to 0, we sum both sides of this inequality from k equals 0 up to, well, k. So that way, the vk's, they cancel out, they form a telescoping sum, so they cancel out. So the sk, that we have the sum of sk's on the right-hand side, but we can move that to the left. So we have the sum of sk's. And then all of these v's will cancel out except v0. So v0 will be here. And then the vk plus 1 will be here, so we move that over here. So by summing on both sides from 0 to k, we get this. And now note that v0 minus vk plus 1, well, that's less than or equal to vk. And then okay, so the sum of the s's is less than or equal to v0. And then we take the limit of k goes to infinity. So the sum of all the s's is less than or equal to v0. And v0 is assumed to be a finite number. So when this holds, when the sum of the s's are finite, we say the sequence is a summable sequence. And a summable sequence implies that the sequence must converge to 0, because the s's are non-negative. The s's never become negative. So if the s's don't converge to 0, then this sum must be infinite, and that's a contradiction. So in this line of argument, we say the vk's is a Lyapunov function, and we say the sk is the summable term. And this argument, this type of argument, where we establish this inequality and thereby conclude that the s's converge to 0, this is referred to as the summability argument. In a way, this is a somewhat indirect argument, and I'm not sure if this kind of argument appears outside of the context of monotone operator theory and optimization. But I think it's not that intuitive, because when the goal is if our goal is to show that sk converges to 0, instead of directly analyzing sk, our first step is to establish the vk's and then show this inequality. And then by showing that the sum is finite, we conclude that the s's converge to 0. So it's a very indirect argument, but it is a standard argument in optimization and monotone operator theory. And let me show you this argument being used concretely. Okay, let's prove Theorem 1. So the proof of Theorem 1 will consist of 3 stages. So let's start with stage 1. In stage 1, we first note this identity. So this identity, this identity is perhaps not obvious, but to verify this identity, what you do is you just expand the square on both sides and verify that everything cancels out. So this identity can be verified through elementary, albeit somewhat tedious, just calculations. Okay, and then the operator t is defined to be an averaged operator. That means t can be written as this convex combination between the identity operator and a non-expansive operator s. Then, when we have a fixed point iteration with respect to the operator t, we can instead express it in this way. So we plug in t is equal to 1 minus theta I plus theta s. So we get the xk here we have a convex combination of the xk with theta s of xk. When we do this, now we let x star then be any fixed point of our operator t, and then we bound the distance, then we establish a bound on the distance of xk plus 1 to the solution. So xk plus 1 is defined by definition equal to this. So we take this and just plug it into here. And then we plug that into here, and then we take this identity and use it here. So that gives us this stuff. Okay. Now remember, sk is a non-expansive operator. So, and also it's here we have x star, but the operator s and the operator t, they share the same set of fixed points. So we can easily just write s over here. And then by non-expansiveness, well, this thing is less than or equal to xk minus x star. And we keep this term the same. Okay. And now, well, this norm squared and this norm squared is the same, so we just add these two, and we get this part. And then this part, we just write that down here. Okay, so we have this inequality, and now in this inequality, we have this summability argument arising. On the left-hand side, we have vk plus 1, and then we have this term, and we call this term vk, and then this term serves as the summable term. Okay, so all right. So to rewrite the core inequality is vk plus 1 is equal to vk minus sk, where vk is norm of xk minus x star. Okay, now let's establish. So the statement of theorem 1 had several claims. Let's prove the claim regarding the monotonic decreases. So this core inequality, this is inequality number 1 written in this alternate form. This core inequality establishes that the vk's are non-increasing. So indeed, the vk's are non-increasing. Then we take this inequality, and since this inequality holds for any fixed point x star, we minimize both sides with respect to the x stars within the fixed point of t. So we minimize this side, we minimize this side, and the minimum, since the minimum of x minus x star of x star is in fixed point t, is by definition dist of x of fixed point t. Well, minimizing both sides, we get the distance of xk plus 1 to the fixed point set. That's less than or equal to the distance of xk to the fixed point set. And this property is referred to as the Theorem monotonicity property. Okay, next let's show that the fixed point residual is non-increasing. So note that this is referred to as the fixed point residual, and t of xk minus xk, because if xk were a fixed point, then this difference would be 0. But when we have not yet converged, when we are not yet at a fixed point, then the difference will not be 0. And therefore, we refer to this as the fixed point residual. Well, this fixed point residual is just by definition xk plus 1 minus xk. So we can view the norm of this fixed point residual as a measure of optimality for the fixed point iteration. And since the operator t is non-expansive, well, xk plus 1 minus x, that's equal to, well, xk plus 1 is txk, xk is txk minus 1. We apply non-expansiveness, so the subsequent fixed point iteration is less than or equal to the previous fixed point residual. Okay, so finally, the fixed point residual is non-increasing. But furthermore, the theorem claims a rate on the fixed point residual. So let's prove that. We sum the core inequality from 0 to k. So this is again the summability inequality summed from 0 to k, and that gives us this, where here we have the summability term. We move this to the left-hand side, move this to the right-hand side, and divide by this term. So we reorganize to get this inequality. Okay, now remember, we just established that this quantity, the fixed point residual, is monotonically decreasing. So that means that, so by the way, this is equal to xj plus 1 minus xj. Right? So we have this term that goes here, but within this sum, because this sequence is monotonically decreasing, the last term is the smallest term. So we can lower bound this sum by the magnitude of the last term multiplied by the number of times number of terms within the summation. This is a summation from 0 to k, so there are k plus 1s in total, and each of the k plus 1 terms are lower bounded by the last term. Hence, we have this lower bound. Okay, and then on the right-hand side, we have this term, but we drop this other negative term, so we have this bound. Finally, we divide both sides by k plus 1, so we get that the fixed point residual is less than or equal to this right-hand side divided by k plus 1. Okay, so that gives us the rate on the fixed point residual. We can also, furthermore, minimize this right-hand side with respect to the to x star, because this inequality holds for any fixed point x star. So we might as well minimize over all possible choices of x star. So that gives us that we have a 1 over k rate, and the constant now depends on the distance of the initial point to the fixed point set. Okay, next we need to establish the sequence convergence. So in Theorem 1, we claimed that xk converges to some fixed point. So let's prove this. Okay, so first we show that the sequence has an accumulation point, and then in the second step we show that this accumulation point is a solution, and finally we show that the sequence actually converges to this single solution. In other words, there's only one accumulation point. Okay, so let's consider any x fixed point for our operator. Then our core inequality applied with this particular fixed point tells us that the xk sequences lies within this compact set. Because if you think about it, what the core inequality tells us, if we ignore the summability term, it tells us that the distance of the iterates to x tilde star is non-increasing. So therefore, the iterates lie within this particular compact set, and therefore the iterates have an accumulation point. In the next step, well, the accumulation point, so here we are calling the accumulation point of our sequence x star, and we don't yet know whether it's a solution. So let's show that x star is in fact a fixed point in step number 2. So the accumulation point x star satisfies this condition, this fixed point residual, because, as we had previously shown, the fixed point residual converges to 0, and the operator t minus I is a continuous operator. Okay, so the our sequence xk has a convergent subsequence converging to x star, but on the convergent subsequence, the fixed point residual converges to 0. So at the limit point x star, because t minus I is a continuous operator, it satisfies this fixed point condition. Finally, we apply our core inequality now with the accumulation point x star. So remember, the core inequality applies to is applicable when x star is for any fixed point x star. But now that we've identified that the accumulation point x star is indeed a fixed point, we use the core inequality with this accumulation point. And this allows us to conclude that since this quantity is monotonically decreasing, and since a subsequence of xk converges to x star, well, this distance to x star therefore has to monotonically decrease to 0. In other words, the entire sequence must converge to x star. Next, let's talk about, or not talk about, the termination criterion. So when you execute the fixed point iteration in practice, you need some sort of termination criterion that allows you to know when to end the iteration. So to put differently, the fixed point iteration will likely be implemented as a while loop, and the while loop requires a condition to determine whether to terminate or continue the while loop body. Since Theorem 1 guarantees that the fixed point residual converges to 0 at rate 1 over k, we can use the fixed point iteration of the fixed point residual less than epsilon, where epsilon is a small tolerance, as a general termination criterion. However, for specific setups, there may be specific and better termination criteria. And when I say better, there may be other termination criteria that are better suited, that better reflect the particular goals for the other specific setups. In practice, to utilize the fixed point iteration in practice, it is absolutely essential that an appropriate termination criterion is chosen. So this is an important issue. However, for the purpose of simplicity in this class, we will avoid the discussion of termination criterion. Okay, so now that we've introduced the necessary machinery, now that we've introduced the notion of fixed point iterations, and we've proven Theorem 1, let's analyze the convergence of a few optimization algorithms. So the first method that we will analyze convergence for is a gradient descent. Let's consider the problem of minimizing a function f of x, where f is CCP and differentiable. In this setup, x is a minimizer if and only if x is a fixed point of this operator, I minus alpha grad f, for any non-zero alpha. The fixed point iteration with respect to this operator can be expressed in this way, and this FPI is referred to as the gradient method or gradient descent, and the parameter alpha is referred to as the step size. Now let's further assume that the CCP function f is L smooth. Then, by coercivity, if we choose alpha to be equal to 2 over L, well, we want to see whether this is non-expansive, and to do so, so this is x minus 2 over L grad fx, and then we have the y minus y plus 2 over L grad fy. So we expand all the terms. So we have x minus y squared, we have grad x grad y squared, and then we have the cross terms. So we have all of this. Now this term is bigger than or equal to 0 due to the coercivity inequality. Therefore, we have this less than equal to norm x minus y. To put it differently, this operator is a non-expansive operator. Therefore, since this is non-expansive, then I minus alpha grad f is averaged for alpha between 0 and 2 over L, because if we have any alpha between 0 and 2 over L, then we can express this operator as an averaged version of this non-expansive operator with the identity where theta is this particular value, and it is strictly less than 1. So therefore, the gradient method with alpha between the step size alpha between 0 and 2 over L, it becomes an averaged fixed point iteration. It becomes an instance of the Krasnoselsky-Man, the KM iteration. This allows us to appeal to Theorem 1 and in particular, we can immediately conclude that the iterates xk converge to a solution x star, and the gradient magnitudes decrease with rate 1 over k. Okay, and furthermore, if the function f is strongly convex, then it's possible to establish that the operator is a contraction, and therefore the iterates will converge to a solution at a faster rate. Let's take a look at another method. So this one is referred to as the forward step method. So the problem we solve is we want to find a zero. We want to find a zero of the operator f, where f maps from Rn to Rn. So again, following the same reasoning as before, an x is a solution to this problem. So x is a zero of the operator f, if and only if x is a fixed point of this operator, I minus alpha f, for any non-zero alpha. And this fixed point iteration is referred to as the forward step method. Following the same reasoning as before, if the operator f is beta cocoercive, and if alpha is between 0 and 2 beta, and if a fixed point exists, then the FPI becomes an average iteration, and we can appeal to Theorem 1 to establish convergence. And also, if f is furthermore strongly monotone and Lipschitz continuous, then we can establish that the forward step method is in fact a contraction. The next method that we'll consider is the dual ascent method. So let's consider the primal dual problem pair, where the primal problem is minimize f of x subject to the linear constraint ax equals b. The dual problem is maximize minus f star composed with minus a transpose minus b transpose u. And these primal dual problem pair are generated by this Lagrangian f of x plus u transpose ax minus b. We'll perform the gradient method on the dual function g. So g is the convex function g is defined to be the negative of the dual objective. So it's f star composed with minus a transpose plus b transpose u. Then the fixed point iteration on the gradient descent operator with the dual function g can be expressed in this way. So this minimization step allows us to compute the gradient of g, and in particular, the gradient computation was characterized in our previous discussion, specifically in page 11. So the fixed point iteration with respect to this gradient descent operator with respect to the dual function g has this form, and it is referred to as the Uzawa method or dual ascent. If the function, a primal function f is mu strongly convex, then this dual function is Lipschitz continuous with parameters sigma max squared over mu, because if f is mu strongly convex, then that means the gradient of f star, that is a 1 over mu Lipschitz continuous operator. So A is Lipschitz continuous with Lipschitz continuity parameter sigma max. Grad f star is Lipschitz continuous with Lipschitz parameter 1 over mu. And then minus A transpose is also Lipschitz continuous with Lipschitz parameter sigma max. Okay, so if f is mu strongly convex, if total duality holds, and if the step size alpha satisfies this condition, then we can show that we conclude that the primal iterate xk converges to x star, and then uk converges to u star. Okay, then that concludes our first lecture on chapter 2. So we introduced the mathematical machinery of set-valued operators and monotone and maximal monotone operators. We then talked about non-expansive, contractive operators. We established convergence for the fixed point iteration with respect to an average operator, and then we saw a few applications of these results in the form of gradient descent, the forward step method, and with dual ascent. In the next lecture, we will complete our discussion of Chapter 2. And in the second lecture for Chapter 2, we'll use the machinery called resolvents to construct more more complicated and more broadly applicable splitting methods, and then we'll analyze their convergence by reducing their convergence to the case of theorem 1.